Hello everyone. In the today's video lecture, we will be discussing about the channel length modulation. Okay, so continuing with the previous videos, what we have discussed on derivation for the current equation for different regions of operation. Okay, so basically we discussed the two different field, that is, one is vertical field, that is voltage VGS. The vertical field is due to the voltage VGS. Corresponding to this, we discussed about the different regions of operation for the MOSFET is accumulation, depletion and inversion. Okay, and we start applying the vertical horizontal field, which is VDS. Horizontal field is due to VDS. After ensuring that the VGS applied is in the inversion region, we start applying the horizontal field, or we start applying varying the VDS, right? Corresponding to this, we have the cutoff region, linear region and saturation region, right? So this is the output characteristics of the MOSFET, the nMOSFET, what we have considered here. So in the previous discussion, we discussed, we derived the current equation for cutoff, considering the cutoff, linear equation and saturation region. So now continuing with the saturation region, we are going to discuss about the channel length modulation in the today's video lecture. Okay. So now what happens when the device is operating in the saturation region? That means for the output characteristics, if we consider for a constant value of VGS, right, that means the vertical field which is already in the inversion region, for this we are varying the VDS. So initially what happens when we start varying the VDS, so the current, output current varies linearly with respect to VDS, right? So now what happens here, when we keep this VGS to be constant, that means in the inversion region of the vertical field, the channel is already formed. After this, what happens? The current will be still 0 if VDS is 0. Okay, because there is no difference in the potential, the channel is already formed, the electrons are present in the channel, but they are immovable ions because your VDS is 0, which corresponds to the cutoff region of operation. Okay, so now when VDS starts increasing, the current also starts increasing. So that means the difference in the potential, that means it has enough strength or the potential for the electron to cross from this PN junction or the junction and move from source terminal to drain terminal, because the drain is positive with respect to reference or ground or source. Okay, so now that is how the current starts increasing, by increasing VDS. And initially when it increases, the VDS is increased, the current ID also increases linearly up to certain voltage. Okay, up to certain voltage means this is the point of interest now for the discussion, which we call it as overdrive voltage, which is equal to VGS minus VTH. Okay, that means when the output voltage, what we are varying VDS, it reaches this overdrive voltage, that is VDS is equal to VGS minus VTH, then what happens? The channel is already at the pinch off. This is pinch off, that means the channel is already modified. Okay, as it is the current is increasing in the linear region of VDS, the channel is started changing its dimension, or the length of the channel has been modified. Okay, so now when it reaches the VDS, which is equal to the VGS minus 1 threshold voltage, it is already at the verge of this point, where if increasing further this VDS greater than VGS minus VTH will cause the channel to get pinched off. Okay, so now when you increase this VDS further, that means even after VGS minus VTH, when it is equal to VGS minus VTH, the channel is modified like this, that means it is already at the pinch off. So if you increase it further, that means if VDS becomes greater than VGS minus VTH, then the channel will change its dimension, or the channel is modified. So now the effective channel is entirely different. So initially the channel length was this, which is L. Okay, this is L. Now it has been modified to this Okay, so this channel which has been modified is L minus delta L. We consider it as L minus delta L. Okay, and if we represent the same, the output characteristics, if you see, corresponding to this saturation region, so this is the small signal model what we draw for the MOSFET, equivalent small signal model representing in a two-port network for the MOSFET. So the gate to source is open because the oxide layer, okay, this COX is means SiO2 has a very large resistance, so the impedance is very high. The Zin of the MOSFET will be infinite, which is represented by the open circuit, and hence your the input current Ig will be 0. Okay, and this is the output current which is a function of VGS, input voltage, as this MOSFET is a voltage controlled current source. So the output current, which is this is represented by the dependent current source, is dependent on input voltage. Okay, so it is voltage controlled current source. Okay, so the output current is controlled by input voltage, which is VGS, and this is the current which is the saturation current equation what we are representing for this the saturation region of MOSFET in the output characteristics shown here. So now even if you increase this after VDS, what happens? The channel, effective channel has been reduced. So now the effective current equation will be mu n COX by 2 W by L. So now the L has, this is the equation, VGS minus VTH whole square. This is the equation. Now this L has been modified from L to L minus delta L. Okay, so this is mu n COX by 2 into W by L minus delta L into VGS minus VTH. Okay, so now I will take this L to be common again. So mu n COX by 2 into W by L, taking L common in the denominator, it becomes 1 minus delta L by L in the denominator. So it becomes VGS minus VTH whole square. Okay, so this is the current equation when VDS is greater than VGS minus VTH. So now this, what happens, the denominator term what we have, 1 minus delta L by L. So this delta L what we are getting, the change in the modified version of the channel length is directly proportional to VDS. It is a function of VDS. Okay, so now this proportionality constant is given by lambda dash into VDS. Okay, this is the proportionality constant lambda dash, and this is nothing but the delta L, that is the change in channel length which has been reduced, is nothing but proportional to VDS. It is reduced by the same factor in which the VDS has been increased. It is proportional to VDS. Okay, so now taking this equation what we have, dividing the L on both sides, delta L by L is equal to lambda dash by L into VDS. Okay, so this we will write it as delta L by L is equal to lambda into VDS. So substituting this in this equation, mu n COX by 2 W by L into 1 divided by lambda into 1 minus lambda into VDS, 1 minus lambda into VDS into VGS minus VTH whole square. Okay, so the denominator term lambda into VDS what we have, we can write it as mu n COX W by L into VGS minus VTH whole square into 1 minus lambda VDS 1 to the power of minus 1. So taking this part of the equation as 1 minus x can be expanded as 1 plus x square plus x cube and so on. Okay, so since this delta L, it is a function of delta L, since delta L is very small, this can be neglected, the higher order can be neglected, and it can be represented as 1 plus x. Okay, so the final equation of this, which is id, can be represented as mu n cox by 2 w by L into VGS minus VTH whole square into 1 plus lambda VDS. So now this is the current equation, modified current equation. We will call it as I dash because this is the current with channel length modification, channel length modulation, and this term is called as represents the channel length modulation, uh, which taking this equation, I will continue with the same. Okay, so here I will consider the equation, that is id dash mu n cox by 2 into w by L VGS minus VTH whole square into 1 plus lambda VDS. Okay, so this what we have is nothing but the same as the saturation current equation what we have represented here. Okay, so we are considering that part as id into 1 plus lambda VDS. This is id dash. Okay, so now if we differentiate this with respect to VDS, now this becomes partial derivation with respect to VDS, delta id dash by delta VDS. So here this term 1 is constant and VDS is the variable. What we get is lambda into id. Okay, and the term delta id by delta VDS is nothing but output conductance. Okay, this is output current and this is output voltage, hence it is output conductance. Okay, which is represented by the channel length modulation which you are getting after increasing VDS greater than VGS minus VTH. That means, so this part of the slope is nothing but your G naught. Okay, and this slope gives you the G naught, which is the inverse of this will be R naught. So R naught is 1 upon G naught, which is output resistance, which we will represent in the small signal model. This id dash now, and this is my R naught. So this is the R naught output resistance corresponding to this current in the saturation region because of this slope, and this channel is modified or slightly increase in the slope is due to this channel length modulation, and this R naught itself represents the channel length modulation for the MOSFET. Okay, and this is the equation what we have. The R naught is lambda times of id. Okay, so now the effect of channel length modulation is considered if channel length modulation effect is considered if lambda is not equal to 0. Okay, so similar to that of early effect of BJT. Okay, so that means in this output characteristics, this is VDS versus ID. So the early effect what we get is extrapolating this characteristics to the negative x-axis to get the value of VA. Okay, and this VA can be the entire slope of this curve. So we can calculate this R0 as VA by ID. Okay, this can also be the expression for calculating the output resistance with the channel length modulation, considering the channel length modulation. Okay, so VA is nothing but extrapolating this the output characteristic to the x-axis in the negative x-axis where it reaches 0. Okay, so this is the another expression for the output resistance. Okay, and another point what I would like to mention here is the transconductance. What we have, GM is nothing but the differentiation of this equation, which is mu n COX W by L into VGS minus VTH. This is the expression of transconductance. GM is equal to Kn, that is, this is Kn into VOV. So this is VOV. Okay, so this is one of the expression of the transconductance, and by rearranging these terms you can also represent this GM as 2 times ID by VOV, that means this overdrive voltage. Okay, and also we can represent this transconductance as 2 times of ID into Kn in a square root. Okay, so these are the different ways of representing the transconductance. Why I am mentioning this here is, so basically this transconductance, the current ID and the overdrive voltage VGS minus VTH. So the DC analysis is basically done between these three parameters. If you know any two of them, you can find out the third one. Okay, basically in the DC analysis we find out the terminal voltages and verify that your VDS is greater than or equal to VGS minus VTH, that is overdrive voltage. If the terminals of the gate, source and drain are connected to any other circuit elements like resistance, we elaborate this as VD minus VS should be greater than or equal to VG minus VS minus VTH. So basically by determining the terminal voltages, we check that whether this condition is satisfied or not. If this condition is satisfied, then the MOSFET is operating in the saturation region. If this VDS is less than VGS minus VTH, then the transistor is operating in linear region, right? So this is how we do the DC analysis for the MOSFET device. Fine. So in the next video lecture we'll be discussing about the DC analysis or some problems on finding the terminal voltages for the MOSFET. Fine. Thank you.